All right, what a great day it is today. I don't know about you, but I was dying yesterday. It was so hot out there. I talked to everyone in the tent next door. I felt bad for them because I'm sure I smelled terrible. Went home, had to take a shower, washed my Firebase shirt for sure to be able to be here today. My name is Doug Stevenson. Welcome. It's great to see a packed room, and for everyone on the live stream, welcome as well. I have sort of an eclectic mix of things to share with you today with respect to Firebase and the Android SDK. So Firebase, as you may have seen, is a suite of integrated products designed to help you develop your app, grow your user base, and earn money. Now, I won't go into all of Firebase. I'll go into some things that I thought was interesting when I sort of helped build and promote Firebase from an Android perspective. So first of all, you should know Firebase works with Play Services. In fact, Firebase for Android is part of Play Services. Firebase is distributed with Play Services, and so it might be interesting to know that from the beginning, if you've tracked Play Services progression, a lot of people like to do APK breakdowns. So the Play Services APK used to be just a single APK with a single DEX with code in it. So everyone knows what this is like. This is just like everyone else's app. Then when Play Services started to grow, we had to do multi-DEX. Now, as you know, DEX has a limit of 65,000 or so referenced methods in it. When you exceed that limit, then you have to start multi-DEXing. So Play Services is just like any other app where it had to do multi-DEXing. Now, Play Services is kind of special in that they have to take very special care to determine which objects go into the main DEX. So the main DEX normally is constructed by the build tools for you, and will pick out the classes in it that need to be in the main DEX. But there are certain things that need to be in there that maybe you have to tell it. So if you're using reflection, or if you're doing anything prior to the creation of multi-DEX, that has to go into the main DEX. And if you have questions about the nuances of how this works, go find the Android office hours. They can help you work through that. Now, when Play Services continued to grow, we found that we needed a more of a modular architecture. So new features of Play Services are now being embedded into the APK as modules. And the value of having modules here is that this lets us do things like independent updates of modules. So in the past, if we wanted to update Play Services, we'd have to do this monolithic APK download, and that took a lot of bandwidth and a lot of time, and it disrupted apps that were trying to use it. So now with this modular interface, we're letting the modules update themselves outside of the normal Play Services release cycle. So what this means for your app is your APK and your code can now link directly into the modules that are in the Firebase or that are in Play Services. So when you use Firebase, a lot of times you're actually referencing code that lives within Play Services. That code is being pulled directly into your app, not physically, but in terms of linking. So you can think of it like kind of like a shared library. Now this is great because now you don't have to go through a binder interface to get things done like you did with Play Services previously. Now, to get Play Services, to get Firebase, you will have to download the latest update Play Services. So be sure to get version 30. This is a screenshot of the standalone updater. Once you have version 30, then you can start developing with Firebase on Android. So the Firebase Gradle plugin, which I guess is more correctly called the Play Services plugin for Android, you might be curious what happens with that plugin. Well, I'll tell you a little bit about what happens. Three things. One, it will read a configuration from your Google Services JSON. So Firebase is just like Play Services was, where you go to a console, you get a JSON file, you drop it into your app. This contains configuration that your app will use in order to operate correctly. And the other two things it will do is inject Maven dependencies. So if you're looking at this bit of code here, it might look a little bit strange. This is actually Groovy code. This is not Java code, so you'll notice the lack of a semicolon and single quotes around some of the strings. So what we're doing here is the plugin will reach into your project, look into its dependencies collection, and add a compile dependency on Firebase Core. Now this Firebase Core module is kind of interesting because it contains no code. Now why would we add a dependency on something that contains no code? That seems kind of weird until you look inside the Maven POM file for this. So a POM file is just sort of metadata about how a dependency works. And you look in the highlighted section here, you can see that the Firebase Core module depends on Firebase Analytics. So when you apply the Google Services plugin to your Firebase app, you will get analytics for free. Now, this is kind of important to note. This is how important we think that analytics is for your app. You get it always. It's a crucial part of Firebase applications. And you'll see that throughout this conference, you'll see how Firebase Analytics actually enhances the capabilities of the other components that you use in your app. The third thing that the plugin will do is inject some resources. So you can see in this bit of code, we're reaching into your project, into the Android configuration, and for each of the variants that you're building, what we'll do is find a unique location for that variant, that's your file output directory, and then we'll create a task. And this task, what it does is it will generate resources when it's called. So on that variant, we can register a resource generating task, pass it that task that will actually do the work, and feed it the output directory. Now what happens here is, this is an API within the Gradle plugin that when it's called, you can say if this plugin wants to generate some resources, this is an output directory that the rest of the build will use to look for those resources. And what this does is it actually drops fully formed, valid Android resource files, XML files, that will be merged into the build. So what all this task is doing is it's reading out of that JSON file all of those values and keys and configurations and storing them as resources. And that's how your app actually gets a hold of all the different things that it needs to operate properly. So if you're developing with Firebase, you'll likely come across this new task API. Now, this is how this is how Play Services is doing concurrency within your app. So this is like the API that pretty much all products will be using going forward. This is created just for Firebase APIs. However, this could be applied to any sort of Play Services API in the future. Now, for Firebase specifically, if you're using remote config, authentication, or file storage, you will run across this task API. So it's an important thing to know. So the general form of the async API is, let's say you have some API and we'll call it Firebase thing, and say you call a method on that, do stuff. Now, this do stuff method, if it wants to do things asynchronously, it will return immediately and generate a task object. And this task object is parameterized by some result type, whatever it wants to generate. So here we just have a task that returns some result. And on that task, this is a representation of background work. On that task, you can register listeners. So you can have a success listener, and then there's a callback in there that will receive the result type when it's been generated. You can register a failure listener, which then receives an exception of whatever happened that caused the task to fail. So that right there is all you actually need to handle these things correctly. Now, there's a third version where you can just register an onComplete listener, and what this does is it bundles both success and failure up into a single callback. And if you choose to use an onComplete listener, what you do is you get a task, and then you can ask that task, did you complete successfully? If you did, give me a result. If you did not complete successfully, well then give me the exception. So you can choose. You can either register success or failure separately and independently, or you can do a completion listener and handle both in the same callback. So there's 4 ways to get task results. I've showed you the general format, but there's 4 different ways, and you should know each one of them. First of all, there's a callback on the main thread. So this is what I just showed you in the previous slide. You can add a success, failure, completion listener, give it a listener, and this listener will be invoked on the main thread. Now, there's a different format, and you should know this one. This is actually more important than the last one, where you can get a callback scoped to an activity. And what it means to be scoped to an activity is this listener that you register will not get executed if the activity goes through its on-stop. So if an activity is being stopped, the listener will be automatically unregistered and it will not execute. Now this is really important because if you register a listener without unregistering it, when the activity dies, you can have an activity leak, and that's terrible. Long-running tasks that exceed or go beyond the life cycle of an activity can cause a leak. This causes out-of-memory problems, and they're actually very difficult to diagnose. So if you're calling this API within an activity, use the second format. Use the format where it accepts an activity object, and you only register or only have that listener for that one activity. Now, if you want to receive your result on another thread, so not on the main thread, if you want to handle something in the background thread and say you want to do more blocking work after that, you can feed an executor to the task listener. Now, if you've never dealt with an executor before, it's basically a Java or a JVM construct that identifies a thread to do work on. So the executor will make a decision and say, how do I deploy this to another thread? It could be just a single thread, or it could be a pool of threads, or it could be a growing and shrinking pool of threads. This API doesn't care. The executor cares where the thread goes. You just hand it an executor that makes that decision. And the last way is you can actually just block the current thread if you want to wait for the result in line. Now, I say right away, don't do this on the main thread. Don't block the main thread. We can't say that enough. Don't do that in your Android applications. It can lead to a fairly bad user experience. But if you do want to block some other thread, there's a utility method on tasks called await. And you can call tasks await, give it the task that you want to wait for, it will block, and then the result will come out of that. Now, if you're not willing to wait indefinitely, you can feed it a timeout, and that timeout will sort of time box the amount of time you're willing to wait, and it will return with an execution exception. Now, you will have to catch both an execution exception if the task fails, or an interrupted exception if the thread is interrupted. So you'll have to handle that case here. So let's say, how do you do a sequence of work? Now this can be common in some Android apps where you have task 1, which leads to task 2, and so on and so forth. You have to do them in order. There's a special way to express this in the task API using continue with or using continue with task. And there's a subtle difference between the two, and I'll unpack those right now. So if you're using continue with, you will have to create a continuation object. And what a continuation object does is it says, I know how to, there's some result type for input, and there's some result type for output. And within my method, when it's called the then, within the then method, it receives the task that's generating the input type. So you can see inside the method, we're calling task.getResult. That returns the input type. Then we can do some transformations on it, do whatever we need to do, and then generate an output type in response. And to make use of that, you just call, on the origin task, you call task continue with, feed it the continuation, and that feeds you yet another task, which is parameterized by the output type. Now, if you're using continuous task, it's very similar but slightly different in that continue with task generates a task. It doesn't generate the result type directly. It generates a task that is responsible for generating the output type. And the format for execution is just the same, task.continue with task. It returns a task object that you can then wait on to get these results. Now, it begs the question, oh, no, I'm on the wrong slide. OK, so the upshot of all this task chaining business is that you have a sort of syntactic sugar for executing a series of tasks. So if you're like me and you've worked with data processing frameworks like Spark, you know that you have a series of steps that you have to execute. So say, for example, you have a query, and that's going to generate a result set. Then you want to filter, and maybe do some mapping, so translate from one data type to another, sort those results, and group them by type. You can express that very succinctly like this. So this is how you do serialized chain of execution. So if you want to do parallel task execution, and I would say this is actually more common than serial task execution. If you want to do it in parallel, and this is very common if you say want to kick off, I don't know, an authentication and a query and do a database read, and you want those all to happen at the same time, but you only want to progress to the next step when all of those are complete. So you only want to wait as long as the longest one of those tasks. So to run things in parallel, you can use tasks.winAll. So tasks, again, is a utility class. WinAll is a utility method that says, I'll take each one of the tasks that you want to wait on, and I'll generate from that a final task. Now, this is asynchronous. You'll get a task in response asynchronously, parameterized by void. It itself doesn't generate anything, but it gives you a target to listen to know when all the tasks are complete. So on this final task, you add a success listener, and inside there, you can reach into all the other tasks that were in flight and get their results. Now, it's worth noting that if any one of these tasks fail, the entire thing will fail. So you'll need to check for that as well. Same thing with serial task execution. If any one of your tasks in the serial chain fails, the whole thing will fail. And in fact, that exception will get propagated on from task to task until the final result will receive the original exception that caused the failure. OK, so the easiest way to create your own task is to create what's called a callable. And if you've never dealt with a callable, it's a Java construct, very similar to runnable. So runnable takes nothing as input and generates nothing as output, but callable takes nothing as input and generates some parameterized type as output. So in this case right here, we're creating a callable, it's parameterized by some result type, and it simply returns that result type. So put your work in a callable, and then all you do is call tasks.call, and then you feed it that callable. And immediately you'll get a task object that is that you can wait on to get that result. Now, it's important to note that tasks.call will schedule your work to run on the main thread. So if you're doing some blocking work in your callable, you probably don't want that. You probably want to schedule that on another thread. And again, there's a format that takes an executor. So create an executor, schedule your work on that, schedule your task on that, and then you can use that task in serial or parallel tasks along with the Firebase tasks. So now, if you have your own threading framework, and I know there's a bunch of them out there, and everyone has their own, favorite asynchronous threading framework, you don't have to abandon that to use tasks, and you don't have to wedge tasks into that other format. There's a way to do some interoperability, and there's a bunch of code on this, and I'll try to unpack it. So the interop method here, or the class here, is called task completion source. And what a task completion source does is it provides kind of an empty task for other threads to feed their results into. So when you have a task completion source, you can get a task out of it and then register a success listener. And then that success listener will again be parameterized by the type that you're expecting. Now, in this example, below that, I'm going to fire up a new thread. Now, you shouldn't do this in an Android app, but this is here just for illustration. What you can do is, in that other thread, whatever it's doing, if it's going to generate some result and you need to feed that result into a task, you can just call source.setResult. And what that does is the task that's in that result will then be fully completed or fully resolved. And so that's how you can have things in your other asynchronous framework work with the task framework. So that's all great. Now I'd like to move on to some specific product details. So I'll tell you a little bit about Firebase crash reporting. Now, crash reporting is special to me because I actually worked on this. Like, this was, I'm actually the developer advocate for crash reporting in Test Lab. And so I have a sort of special place for me with crash reporting. So you might ask the question, how do you actually detect a crash? That seems like a strange thing. How do you do it? So I'm sure you all know this dialog. If you're an Android developer, you have seen this dialog. If you haven't seen this dialog, I'm willing to bet you've never written a line of Android code, or you're a really darn good developer. So, and actually, I think this dialog is actually kind of funny because it's saying something rather unfortunate happened, and I'm asked to be okay with it. Now, I don't think this is okay. This is not okay. So the button should actually say not okay. I really think it should say not okay. But in this case, I'm being asked to say that it's okay. And then when you push okay, then the process finally dies. So the way to handle this case is using something called an uncaught exception handler. And this is a regular Java construct. This is an interface under Java lang thread. You can register one of these, and this will get notified if there's an exception that popped off the call stack. So if there was usually a runtime exception, more often than not a null pointer exception, that made its way all the way back to the top of the call stack, and you want to know if that happened, use an uncaught exception handler. So the interface for that is pretty simple. Here I'm creating an anonymous uncaught exception handler. I'm going to receive the thread that actually generated that and the throwable that made it outside the call stack. And then what I can do is to register this for all threads within my JVM, or ART or Dalvik or whatever you want to call it. You can call set default uncaught exception handler, a great verbose Java name, pass it that handler, and then what happens is anytime for any thread, if it's going to crash with an exception, you'll get called before the process finally dies. Now, actually, I advanced a little too soon. So if you register an uncaught exception handler, that does nothing. So like in the previous slide, there was no implementation there. If you register that, it will actually keep your app from crashing. It will continue to run, which is probably not what you want, because if a runtime exception gets thrown, that will actually, that's a bad thing for your app. It really should die. Things could be in a bad state. You don't want to continue. So what you really want to do is call through to the prior exception handler. So this is the best practice. This is kind of the understood practice for exception handlers. So the first thing you do, you get the prior default exception handler. Then you create your own and call through to the prior one when you're done. This lets a bunch of components all create a different sort of like chain of, not chain of responsibility, but a chain of action. So you can register a bunch of default exception handlers. Each one of them will run in turn until the original default exception handler, the Android exception handler, which is responsible for putting up that, the crash dialog, will finally run. So you've probably seen this as well. This is an ANR, or application not responding. This happens when you run something on the main thread that takes more than 5 seconds, and more often than not, then that's some sort of like network access or file access that took too long, or some sort of algorithm that got out of control. This is a bad user experience. Again, it's asking me to be okay with that. I'm not really okay with it, and I probably don't want to wait. But this is not generated from an uncaught exception handler. This is Android kicking in and said, look, your main thread is out of order. The user needs to be able to decide, do I want to keep waiting for this? Now, it's worth noting that inside your default uncaught exception handler, if you block too long in Android, you can still ANR the app. So your uncaught exception handlers still have to follow the general rules of Android development where you don't block it. It's kind of a bad idea. And if you do block for more than 5 seconds and the user chooses to terminate the app by saying, OK, you'll lose that crash. The Android as a platform will kill your app. So in your uncaught exception handler, you need to be quick. You need to get out and let that app crash and let the user move on. Okay, so all that aside, now hold that all in your mind for a moment and say, now let's talk about how crash reporting actually works. So at some point, we need to register this uncaught exception handler. Crash reporting needs to do this. And we use a content provider for this. Now that seems weird. Why would you use a content provider to register crash reporting? Isn't a content provider supposed to provide content? And you would say, yeah, of course, a content provider is supposed to provide content. But there's some interesting properties about content providers that make this interesting. And it's worth a while to look at how an Android process actually starts up. So there's a procedure that every Android app goes through. So the first thing that happens when an Android process starts up is every content provider that you declare in your manifest goes through its onCreate in order of priority. So if there's a priority definition there, it will go in that order. Now, it's also worth noting that this happens in your main process only. If you have a multi-process app, and most of you probably do not, but if you have a multi-process app, this process, the content providers will not be created off the main process. The second thing that happens is your application subclass will be created. So if you've defined an application subclass, which I think something like 1/3 of all Android apps do this, that will be initialized, go through its onCreate after all the content providers. Then once that happened, the third thing that happens is whatever component that needs to be invoked will be invoked. So usually it's an app launch, and so an activity will come into play, or a service could have been started, or a broadcast receiver. Whatever the invoked component is, it will not be created and run until content providers and applications all init. So it's worth noting here, content provider is the earliest hook into the Android process, right? So that's why we initialize crash reporting there. If we initialize crash reporting in a content provider, that means we will happen before application and before everything else. So that's one benefit. The other benefit to using a content provider is that content providers participate in Android manifest merger. So in Android, you know that if you have library projects and all of those things from all of those manifests all get combined into a single manifest for your app. So if we define in our crash reporting library a content provider that does init, that automatically gets pulled into your app, and that automatically causes initialization. Now, this is great because you don't have to write a line of code to initialize. All you do is depend on the library, and manifest merger will bring our content provider in, do the initialization, and it's super easy for you. Now, the reason, now you say, couldn't you use application for that? Well, you could use application, but applications don't participate in Android manifest merger. The only way you can define an application object is you and your manifest. Library projects cannot contribute to applications. They can't hook into onCreate, so that's why we're using content provider. Now, the Firebase uncaught exception handler does a number of things. The first thing it does is it collects a lot of information about the device. So this is when we go off and find the device type and measure memory and serialize the exception. And what we're going to do is dump that all into a protobuf and send that to a crash service. Now, the crash service is an Android service, and the way we built it, at least for launch, for this launch, is to run in another process. So the crash services that do persistence of the crash, so we'll write it to disk and do the transmission, all happens in another process. Now this is a clever idea, right? If you remember back before, you can say, the idea of causing an ANR within your crash handler is a bad idea, so what we wanted to do is get all that data as fast as possible and ship it off to another process, let that do the blocking, let that do the writing to disk, let that do the writing to network, and then let the main app process crash gracefully and let the user move on and do what they want. This also lets us do persistent retries, so this other process can go and keep retrying and sending that crash so we can get it as fast as possible. Now, there's a little problem with this scheme. So let's look at what the problem is. Now, I don't know if you can see it right away. We didn't see it until late in the development cycle, and I'll say a little bit more about that. But here's the situation we have. We have a main app process, and it goes through its content provider, it goes through its application, and it goes through its invoked components. Now, we have this background process that's handling the crash. It goes through its application init, and the crash service gets invoked. The problem here is that if your application object is writing to some shared resource, to a database or to a file, there's a potential for a race conflict here. Most app developers don't actually depend or expect that their application object would be run twice. The normal expectation is that it's run once in a single process, but because we're running crash reporting in another process, that means we have a second application object just like the first, and it's doing the same thing as the first. So if your application object is writing to a database, you could actually run into a locking problem. So we actually didn't detect this. The people who detected this were our early access partners. We had a couple partners who had some strange errors, and we couldn't figure it out, and it turned out this was the problem. And this is one of the reasons why we're launching crash reporting for Android as beta, because of this. Now, it should be told that crash reporting is, it's production ready. We want you to use it. We really hope you use it. We think it's a great tool. But you should know if your application object is doing any of this writing to a database or writing to a file, crash reporting may cause problems for you. And this is something we're hoping to resolve. Now, there's another problem with this plan of using a background task, is that there's a movement within Google to encourage apps to eliminate background invisible work. Now, I'll define what invisible work is. Invisible work is something your app is doing without a UI displaying. So if you have no activity that started in the foreground, so that would be visible work. Or if you have a service that has a notification in the curtain, that's visible work. So if you don't have either one of those situations, that's invisible work. And at Google, we're trying to encourage developers to cut back on the amount of invisible work, because that can cause battery drain or unknown like data usage. So for crash reporting, this actually we're doing invisible work. So we need to cut down on that. Now, I was expecting to have a URL to a blog post where we talk a little bit more about that. Unfortunately, it's not available. I'll have that on Monday. I think the plan is to publish this on Monday. So if you join the spaces for this talk, I can get you that URL. I think it will be posted on our Medium blog. So if you want to read more about that, follow up with that. So in the next version of crash reporting, we will actually not have a background process. We're working on eliminating that. The upsides, of course, it will work more widely, so we don't have to worry about apps with application objects that aren't compatible. And it'll be more compliant to development trends. We'll be cutting back on this invisible work. The downside is that there is an increased chance of latency. So with the old solution, we could be fairly certain that we could get that crash packaged and sent very quickly. But if we're competing with the idea that the app may die before we can get the crash, out of the, into our servers and out of the app, there's just a risk that we just can't get it immediately. And also this gives us a sort of constraint of being able to retry less frequently. So that said, there's trade-offs. We're going for the no background process version. Okay, so that's crash reporting. I'll say a little bit about how things work on, oh, it didn't advance. Firebase Analytics, okay. So another interesting thing, you might be wondering, how does Firebase Analytics track user behavior? Now, if you recall earlier, we put analytics in every Firebase app. This is a very important component. And what it does, one of the things it does, is it tracks the usage for your app. Now, this is great. You do nothing. You actually write 0 lines of code, and you get tracking. And you might be wondering, well, how does Analytics actually do that? If you're not writing code, how does it reach into my app and know how the user is using it? So the question that we're trying to ask is, how do we determine when the app is in the foreground and when the app is in the background? How do you track the time spent in the app, and how do they navigate activities? And this is useful for determining things like how long a session is, or how frequently a user is using your app. Now, the way we do that is using something called activity lifecycle callbacks. This is an API in Android. It's available since Ice Cream Sandwich and beyond, so API level 14. If you create one of these and register it with your app, you can receive callbacks for every activity in your app. So this is like a universal listener for all activities. So all activities clearly have to go through their create, start, resume, and so forth. You can listen to every single one of those. And this is how Firebase Analytics determines how users are using your app. So for this interface, we have created, started, resumed, paused, stopped, destroyed, and save instance state. You can listen to all of these, but there's two in particular that are of interest to us in determining how a user is using your app, and that is onStart and onStop. So here's a bit of code. It's kind of it's a little bit pseudo-codey, but this is something you could actually do in your own app if you want to track something similar. So I'll walk you through these lines of code. So the first thing we want to do is count the number of activities that have been started. So that's num started. We also want to count the moment at which the user first enters the app, and that's user entered time. Now, when we listen to onActivityStarted, what we can do is say, if there are no activities currently started, so num started equals 0, what we can do is record the current time, and that's the time that the user launched the app or first entered it from, say, the task switcher. And then what we do is we increment the number of started activities. Then, as an activity is stopped, we'll turn around, decrement the number of started activities, and say, if the number of started activities is 0, meaning there's no activities visible right now, record the time that they left the app, do a little math, and say, this is how long the user was in the app. Now, this is pretty handy, right? This is a fairly bulletproof way of knowing when the user was looking at your app and when they were not, because as long as you have an activity started, you can be certain that you were on the screen. When your activity is stopped, you can be certain that you were invisible. So this is how we track that. So what's next after here? So I've given a bunch of information. I hope you found it useful. Now, if you're an iOS developer, there's another talk in this room after lunch from an iOS perspective. If you have questions, you want to know anything about Firebase, there's links here. And if you want to join the space and ask questions and interact with each other, and I have that link to the blog post, that'll be here as well. So it looks like we have some amount of time left. I'll take some questions if anyone would like it, and thank you for being here.